Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss resonance and stability of benzene. Resonance and stability of benzene. According to valence bond theory, the concept of oscillating double bonds in benzene is now explained by resonance. Benzene is a hybrid of various resonating structures. The two structures already I have discussed, that alternate double and single bond. That is the first structure. Suppose you start with the double bond, then that is the first structure, and when you start with the single bond, then it is the second structure. Means structure A, if you start from the double bond, single bond, double bond, single bond, double bond, single bond, means 3 double bond, 3 single bond. That is a structure 1. Structure 2, when you start with single bond, double bond, single bond, double bond, single bond, double bond. That is a structure 2. And finally one structure you can write, resonating structure, that is the inside the benzene ring, one dot circle you can write, or one circle you can write. Then this I told about the 2 structure. Then this 2 structure is given by K. The 2 structure first and second, that is given by K. And these are the main contributing structure. These 2 structures given by K. are the main contributing structure. The hybrid structure is represented by inserting a circle or a dotted circle in the hexagon. Okay. The circle represents the 6 electrons which are delocalized between the 6 carbon atoms of the benzene ring. Means they are not fixed, they are delocalized, means moving. That's why circle sign is given. The orbital overlapping gives us better pictures about the structure of benzene. The orbital overlapping, here you have to understand, the orbital overlapping gives us better picture about the structure of benzene. All the 6 carbon atoms in benzene are sp2 hybridized. sp2 hybridized. 2 sp2 hybrid orbitals of each carbon atom overlap with sp2 orbital of adjacent carbon atoms to form 6 cc sigma bond, which are in the hexagonal plane. Again you understand, 6 carbons are there in benzene ring, hexagonal. All the 6 carbon atoms in benzene are sp2 hybridized, all 6 carbon. Okay. And these 2 sp2 hybrid orbitals of each carbon 2 sp2 orbital, one left side, other right side. Both sp2 hybrid orbitals of each carbon atoms overlap with sp2 hybrid orbitals of adjacent carbon atoms. Left side also, right side also. Every carbon sp2 hybridized orbitals are there. And 2 sp2 hybrid orbitals of each carbon, one each, they will overlap and they will make a sigma bond. Then there are 6 carbons and 6 sigma bonds will be there. Okay. Then this is very, very important to understand. The 6 carbon sigma bonds which are in the hexagonal plane, or this six, all these C sigma bond are in hexagonal plane. Means 6 bond ring formed. This six carbon sigma bonds are in the ring form. That's why it is called hexagonal. Hexagonal. Now the remaining sp2 hybrid orbitals of each carbon, 2 you have used. Each carbon 2 sp2 hybrid orbitals. This sp2 hybrid orbitals of each carbon you have used in making 6 carbon sigma bond. Now on each carbon one hybridized actually sp2, 3 sp2 hybrid orbitals are there. Then 2 you have used, 2 orbitals you have used, then third one is remaining, and that sp2 orbital will make overlapping with H bond S orbital. Already I have discussed in the case of ethylene. Same thing there. Now one remaining sp2 orbitals will make bond with S orbital of H. Then 6 HCH bond will be formed. sp2s. This is also sigma bond will be formed with 6 hydrogen. Each carbon and hydrogen one bond, sp2 and S. This now all sp2, all 3 sp2 orbitals of carbon is finished. Correct? Now you have to understand here, that is important things. That now on each carbon one unhybridized orbital is there. Already you know in during ethylene and ethine I have told you, ethine 2 orbitals are remaining, and here 1 orbitals. In ethene 1 orbital, ethine 2 orbital, and alkane actually sp3 1 was there, 1 hybridized orbital. Okay, not in alkane, no. Alkane all are sp3, nothing is remaining, 4 sp3, but alkane 1 is unhybridized, that's why they are making 1 pi bond, and in ethine triple bond 2 unhybridized orbital, that's why they have made double 2 pi bond, total 3 in ethine and 2 in ethene. Here now 1 unhybridized p orbital is there on each carbon. Then now what will happen on this you can say this unhybridized p orbital, again they will make I can say bond with adjacent unhybridized p orbital. Two unhybridized p orbital adjacent, because they are very close, they can overlap and they will make a sigma they will make a pi bond. Each unhybridized p orbital they will overlap because they are close enough to make a pi bond. Okay, because electrons are moving up and down. Dumbbell, you know that dumbbell structure is their p orbital. Electrons sometimes electron will be up, sometimes down. Like that way they will overlap, and because they are parallel, both are parallel, hence both will overlap and make a pi bond. Then like that way, now 2 carbon make 2 carbon at a 2 carbon this unhybridized p orbitals was there, and both overlapped and made a pi bond. Like that way Like that way total 6 carbons are there. Then other two again adjacent carbon, again adjacent to carbon, again they can make a pi bond. Then total 3 pi bond will be formed. Okay, if you will give the numbering 1, 2, 3, 4, 5, 6, then carbon number 1 and carbon number 2 adjacent, they have made 1 pi bond. After that 1, 2 already used, now 3 and 4, not 2, 3, 3 and 4, because 1, 2 already used. Then now carbon number 3 and carbon number 4, 1 unhybridized p orbitals are there, and these orbitals will overlap and they will make second pi bond. Okay, now again 3, 4 you have used, then 4, 5 will not overlap because already 3 and 4 both have used. Now 5 and 6, carbon number 5 and carbon number 6, unhybridized pi orbitals, they will overlap and they will make a, this is actually sidewise overlapping, or you can tell lateral overlapping. Then these two 5 and 6 unhybridized p orbital, they will sidewise overlapping, they will do, and they will make pi bond. Then 3 pi bond formed. First and second carbon atom formed 1 pi bond. Then third and fourth carbon, again 5 and 6. Okay, because 1, 1 only they have unhybridized p orbital, only 1, 1. Carbon number 1, carbon number 2. They made 1 pi bond. Now they have used up. Now third and fourth, they have made their pi bond is unhybridized p orbital also used up. Now fifth and sixth. Then like that way, now they made 3 single bond and 3 double bond. Correct? In the beginning, sp2, 6 bond they formed, all were sigma. Now 3 pi bond they formed. Alternate pi bond is there, sigma, pi, sigma bond. Or single bond, double bond, single bond, single bond. Single bond, double bond, single bond, double bond, single bond, double bond. Hence, now it became a ring having double and single bond, alternate double and single bond. 3 double bond, 3 single bond. Okay. Then now this I have told you that they have made, you can say, total 3 single bond and 2 and 3 single bond and 3 double bond. C1, C2, C3, C4, C5, C6. These are the 3 single bond, and C2, C3, C4, C5 and C6, C1. Okay, these are the double bond. And there is not this thing fixed that only 1 and 2 will make a double bond, because near the 1, 2 adjacents are there. 2 is also there, 6 is also there. Adjacent to 1, carbon number 2 is also there, carbon number 6 is also there. You can, left side also you can count 1, 2, 3, 4, 5, 6, again 1. Then this carbon 1, that adjacent to carbon 1 time it is 2 also right away, and left way 6 is there. Hence it is not necessary that they will make bond, double bond, means pi bond only with 1 and 2. They can make 1 and 6 also. 1 and 6 also. Correct? Like that way this will apply for all carbon. 6, 1 and 6, and then 2 and 3. Correct? 1 and 6, 2 and 3, 4 and 5. What was left out in the first time? Second time, that also it can make, because that is also adjacent. That is Not only 2 is adjacent, 6 is also adjacent, and second possibility is to make with the second possibility is also. Now it will go in a reverse way. Where was his first single bond? Now it will become double bond. Where was double bond? There will be single bond. Wherever it was a single bond, now they can make double bond also, because that is also closest, adjacent. Correct? Just like near the 1, 2 and 6, both were closest. Then they can make with 1, 6 also. Like same way with carbon 2. With carbon number 2, 1 is also close and 3 is also close. Then now they can make with the 3 also. 3 also. Like that way, 4. Near the 4, 3 is also close and 5th is also close. Like that way, they can make both sides a double bond. Double bond means pi bond. Hence, because 2 possibilities are there, hence and electrons are revolving, moving. That's why it can form alternate single and double bond. That's why circle sign is given. Now I have told you about this calculus structure and formation of single and double bond in benzene ring. Calculus structure with a localized pi bond. Two calculus structure already I told you with localized pi bonds. Okay, it is forming the internuclear distance. How will you see what is the distance between the carbon-carbon bond? The internuclear distance between all the carbon atoms in the ring has been determined by the X-ray diffraction. By the use of X-ray diffraction, this distance can be measured, and it is found to be the same. All that now if you write the ring like inside a ring structure, inside circle, that time you will see this by X-ray diffraction it was found that bond length of all six bond have same energy as the same bond length. It has been determined by the X-ray diffraction that bond length is same. There is a equal probability for p orbitals of each carbon atom to overlap with the p orbitals of adjacent carbon atoms. That's why third structure you can write as a C. Third structure, first, second, third structure you can write like a ring inside one circle. And this can be represented in the form of two dot nuts rings, means 50% up, 50% down, because electron will be moving up and down. Then dumbbell structure is there, then half dumbbell up and half bell down like this. Dumbbell means half from the carbon it is going up, again it is coming down. Then there will be total three plane type. You will feel there are 3 type of plane. One is for carbon, other is going up, perpendicular, up and down also. Then 50% up, 50% down, then 50% up it can show as a ring, and 50% down also you can show as a ring. That is called dot nuts. Okay, dot nuts of electron cloud, one above and one below the plane of the hexagonal. One above and one below the plane of the hexagonal ring. Hexagonal ring, carbon hexagonal ring is in the middle, and it will be, you can say, one up and one up, one down. Okay, dot nuts ring have electron density clouds. Electron clouds you can tell. Electron clouds. one above and one below the plane of the hexagonal ring. I will try to send this structure. Now again you can see more about this benzene structure. The 6 pi electrons are thus delocalized and can move freely about the 6 carbon nuclei instead of any 2. See, actually K structure, what he told that time, double bond, single bond, he told. It is moving told, but it will make resonating structure. He didn't tell about that things. About the resonating structure, he didn't tell. Then that time, this pi bond was localized in his case. K structure 2 structure, there pi bond was localized between the double bond. But now in resonating structure it is moving. Okay, then that's why here, why it is a special stability for benzene, a special characteristics of benzene. Now you can understand that now these you can say moving electron clouds, they are going to be attracted. They are going to be attracted by nucleus of each carbon. These clouds are going to be attracted by nucleus of each carbon. But K structure, where it was localized between 2 carbon, then they were attracted only by that 2 carbon. That electrons were attracted only by 2 carbon, not by all. Okay, but here now, because electrons are moving, clouds are moving, then they are going to be attracted by all 6 carbon nucleus. That's why it is more stable. And that K structure 1 and 2, that was less stable. That's why he was not able to tell about the special stability of benzene. Okay, the delocalized pi electrons cloud is attached more strongly by the nuclei of the carbon atoms than the electron cloud localized between 2 carbon atoms, as was the case of K. Here special stability means why it is strong, then this is due to the delocalized pi electrons cloud is attracted more strongly by the nuclei of the carbon atoms than the electron cloud localized between 2 carbon atoms. Therefore, presence of delocalized pi electrons in benzene makes it more stable than the hypothetical cyclohexatriene. That was the hypothetical. Cyclohexa, tri means 3 in double bond. Okay, it is more stable than the hypothetical cyclohexatriene. X-ray diffraction data, again you understand more. X-ray diffraction data reveals that benzene is a planar molecule. Okay, and that is 2 types of carbon-carbon bond lengths were expected. Correct? 2 types. However, X-ray data indicate that all the 6 carbon-carbon bond length are of the same order, means 130 picometer, 139 picometer, which is intermediate between double bond and single bond. What was the wavelength? They are intermediate, means a carbon-carbon single bond 154 picometer and carbon-carbon double bond, its bond length is 133 picometer. Then average of these two, 154 plus 133 divided by 2, it is coming 139. That is why any bond length in benzene ring, that is resonating structure I am talking about, it is 139 picometer. All bond lengths are equal. Okay, in hybrid benzene structure I am talking about. But in K structure, both single and double bond was there. One was having 154 single bond, and other was double bond was having 133. Two type of bond was there in K structure. But now here in the resonating structure, all bonds are equal, and its bond length is 139 picometer. Thus, the absence of pure double in benzene. Thus, the absence of pure double bond in benzene accounts for the reluctance of benzene to show addition reaction under the normal condition. It will not show. It will double bond. There it was showing when it was double bond in K structure, but now it will not show. Benzene addition reaction will not take place easily. Reluctance, they don't want to can say this addition reaction. But in extraordinary condition, in resonating structure also, in hybrid structure of this benzene, it can go addition reaction also, but in a special extraordinary condition, not in a ordinary way. But in K structure, they can go by that way, ordinary also. This is the things, because now why they are not they don't want to form addition reaction, because now everywhere bond length is equal. Then this in normal condition it will not go for addition reaction, but in extraordinary condition, benzene now in this hybrid structure, it can go addition also. Okay, thus explaining the unusual behavior of benzene. Now I am going to tell about aromaticity. Generally, all will think that benzene is only aromatic compound. Generally, all will understand that benzene ring is the only aromatic, but it is not like that. Okay, try to understand. Benzene was considered as parent aromatic compound. Now the name is applied to all the ring system, whether or not having benzene ring. This is important. Now the name is applied to all the ring system, whether or not having benzene ring, possessing some characteristics. Aromaticity have some three you can say characteristics are there to show the aromaticity. There are three characteristics, three conditions. If these three conditions in any ring it is present, then that will show aromatic character. What are that three conditions? Then first condition is polarity. Polarity is the first condition. Means it can produce charge, positive or negative charge. Polarity, first condition. Second conditions, condition or characteristics, both you can tell. The first characteristics or condition is the polarity. Second, complete delocalization of pi electrons in the ring. Means any ring, if you can say electrons are delocalized, not fixed, delocalized, moving, then that can show aromaticity. Okay. And third condition, very, very important condition I am telling you, presence of 4n plus 2 pi electrons in the ring. 4n, n means a small n, 4n plus 2 pi electrons. Total pi electrons should be 4n plus 2. Okay, pi electrons, 4n plus 2. This is called Huckel rule. Huckel, Huckel rule. Question is asked. Then presence of 4n plus 2, in bracket you can write pi electrons in the ring when n is an integer. N may have 0, 1, 2, 3, 4, 5 like that way. N is an integer and n value, a small n value is maybe 0, maybe 1, maybe 2, maybe 3, 4 like that way. Okay. Generally it will go 3, 4, not more than that. This rule is called 4n plus 2. That rule is called Huckel rule. Huckel rule. Okay, means pi bond number of pi electrons should be 4n plus 2. Total number of pi electrons. If it is they are following this rule, then that ring will also called aromaticity. That aromatic you can tell. That ring also will show aromaticity property or aromatic property. Example of I am telling you aromatic compound. That is, first example is benzene. Three alternative single and double bond. Okay, 6 carbon atom. That is the benzene having double and single bond. And second is, now it looks like that is first I will tell the name, cyclopentadienyl anion. Cyclo means cycle form. This is the 5 carbon, only 5 carbon. Cyclopenta means 5, di means 2, 2 enyl means 2 double bond is there. In this 5 carbon ring, there is a ring of 5 carbon, but only 2 bond is there, double bond is 2. There is no third bond, double bond. But that fifth carbon, they have one lone pair of electron having negative charge. Fifth carbon have lone pair of electron, 2 electron is there having negative ion. That's why it is called anion. The name has been given cyclopentadienyl anion. Here also you can say double and single. Third one is not a bond, double bond is there, but you can understand. If you will start with the distance single, the single, double in the presence, just in front, double and double in the front. Then if you will see, then if you will start counting single, then double, then single, then now we will come to the fifth carbon. Fifth carbon, just like a fifth carbon, you will make a V type of bond. Then fifth carbon, double bond is there. Then it has capacity to make double bond, one bond. 2 electron means one bond. It can make, but bond is not there. Then double, single, double. Due to this, you can say electron. This lone pair of electron, it can form. It is not making, but can form. Lone pair of electron is there. That you can count as a double. Then again it will become like a double, single, double, single, double, single. But it is a 5 electron ring of 5 carbon. Ring of 5 carbon, and fifth carbon have a lone pair electron having negative charge. Now another example I am giving you, cyclo. Hepta means 7. Hepta trienyl cation. Now you can see the 7 carbons are there. Ring of 7 carbon, and 7th carbon has a positive charge. That's why it is a cation. Positive 7th carbon is a positive charge, hence it is called cation. Then it is a cyclic, that's why you can tell cyclo, and 7 carbons are there, that's why hepta. then cyclohepta, and 3 double bonds are there, that's why 3 double bond is there, then triennyl. Ennyl means here double bond. Then it becomes cycloheptatriennyl cation. Then all show aromatic character. 3 example I given you. All 3 show aromatic character because they are fulfilling these 3 conditions. All 3 conditions, because charge is also developing and electrons are delocalized, and they are this Huckel rule also they are following. Now other example I am telling you, there more than one ring is there. More than one ring is there, and they are also showing these 3 conditions, fulfilling these 3 conditions. Then first example is naphthalene. 2 ring structure is attached. Naphthalene. Okay. If you count from the double bond in both ring, continuously count, then double, single, double, single, double, single, double, single, double, single. Correct? Continuously 2 rings are attached, and everywhere alternate double and single bond is there. Okay. Then here n 2 rings are there. Here you can tell n is equal to 2, and their total number of electrons are 4n plus 2. Then n is equal to 2. Means ring also you can count. N is ring number. N is also telling about the ring number. Then one ring, as for example benzene, 1 was there. Then there 4 plus 2, 6 electron was there. Now 2 ring is there. Then 4n plus 2. Then 4 into 2, 8 plus 2, 10. Then now here 10 pi electrons are there. Third example I am telling you, 3 rings are attached to each other. 3 rings. Its name is anthracene. Then now anthracene, here again if you will count, it will come continuously, can count in all 3 ring. Then you find double, single, 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 double, continuously. Okay. Then here n is equal to 3. Then now total pi electron is 4n plus 3. N is equal to 3. Then 4 into 3, 12 plus 2, 14. Here 14 pi electrons are there. And then this anthracene is in a continuous ring. And if it is in a branch way, means third is attached. Here also 3 rings are there, but third is just like a branch, not in a straight line. Branch it is attached. Then that is called phenanthrene. Then this is also example of aromatic compound. They show aromaticity. Okay. Now I have told about this aromaticity. Now I am going to discuss properties of benzene. Then benzene is commercially isolated from coal tar. You might have heard the name road they are making by the use of coal tar, black color. Benzene is commercially isolated from coal tar. However, it may be prepared in the laboratory by many methods. Then I will tell some important method. One method already you know. That is the polymerization of ethine. Just now only last class I think I discussed this only. Polymerization of ethine. That 3 ethine will join and it will form this thing's benzene. That is called cyclic polymerization. That already know. That red hot iron tube gas have to pass. Okay. Now second actually I am telling you, that is a new decarboxylation of aromatic acids. This is a new lab method. Decarboxylation of aromatic acids. Then here aromatic acid means what? Now onward, when you are studying aromatic compound, then always benzene ring, you generally benzene ring you have to consider, and in benzene ring which group is attached, accordingly name will be given. Okay, if NO2 group is attached, then nitrobenzene. If Cl is attached, one Cl is attached, then chlorobenzene, bromobenzene. If one nitro is there, then nitrobenzene. One Cl is attached, then chlorobenzene. If one bromine is attached, bromobenzene. Like that way, if acid is attached, carboxylic acid, COOH, then that is called carboxylic acid. That is called aromatic acids. Aromatic acid. Then here sodium salt. Now just like acid and base, when it reacts, it forms salt. You know, acid plus base, when it reacts, it forms salt. Like that way, this aromatic acid, when it reacts with base like NOH, in acid H is there, because COOH group is attached with benzene. One H gone, and there in the place of H, COOH has come. Formic acid is H, COOH. Then suppose that H gone and its place that H gone, then it becomes COOH. Okay. Then from the benzene also this one H gone. Then in its place COOH has come. Correct? Then like that way it form benzoic acid, also called aromatic acid. For example, benzoic acid, because COOH carboxylic group is attached with the benzene ring. Okay. Then C6H5 now it becomes C6H5 and COOH group attached. Benzene ring you write, and everywhere double single bond you write, double single. Only with any carbon just COOH group will be attached. Then it is called aromatic acid or benzoic acid. Then this benzoic acid, when it will react with NOH, then COOH, that H and NOH, that OH, it will form water. It will go outside. Then H has gone from the acid, H plus as a go, it went as H plus, then COO become negative. COO become negative. Correct? Then nothing negative, and NO from the NOH, OH minus went as a negative. Then Na became positive, then Na plus, and this COO minus both will join, then it will form salt. Salt, that is called sodium acetate. Here sodium salt of benzoic acid, you can tell. With benzene, acid is attached, COOH, that is why benzoic acid. Now it forms salt. That's why it is called sodium salt of benzoic acid. And you will get this on heating with soda lime with benzene. Benzene you will take, and this things, soda lime means calcium oxide plus NOH. Then if reaction will take place with this, then means benzene plus benzene heating with benzoic acid. Benzoic acid on heating with soda lime gives benzene. Then this is the one way how we will get the benzene plus Na2CO3. Because NOH, Na is there, COO, Na is there. Then it will form Na2CO3. Then from this you got benzene from sodium salt of benzoic acid. Benzoic acid, COONA, you got this is called benzene ring, and COON is attached with this. This is called sodium salt of benzoic acid. Then this acid, from this acid you can get the benzene on heating with I can say calcium oxide and NOH. that is called heating with soda lime, okay, soda lime, that is the NOH plus CaO. Lime means CaO. Then it will give you benzene plus sodium carbonate. Okay. Now other one more method I am telling you, that is the reduction of phenol. Phenol, now you see, now OH group is attached with the benzene ring, and that is called phenol, because phenyl group C6H5 is called phenyl group. One H is not there, then its place OH group is attached. That's why benzene structure right and OH you attached anywhere, and that is called phenol. Then from the phenol you can make the benzene. How will make? Then just to heat with zinc dust, Zn dust, means you are doing reduction of phenol. Then know that removal of oxygen is called reduction. Addition of hydrogen is called this. That you can define oxidation reduction in two ways. First, removal of hydrogen, reduction. Reduction is just reverse of oxidation. Addition of oxygen, that is the oxidation. That addition of oxygen, that is called oxidation, and addition of hydrogen, that is called reduction, addition of hydrogen. And reverse case, if oxygen is going to be removed, then that is also called reduction. Okay, removal of oxygen is also called reduction. Addition is oxidation, removal of reduction. Same way, addition of hydrogen is reduction, and removal of hydrogen is oxidation. Okay, that is the one way to define oxidation reduction. Addition of oxygen is oxidation, and addition of hydrogen is reduction, and reverse case is, that is the removal of oxygen is reduction, and addition of hydrogen is a reduction. And anyhow, other way, electronic concept is very, very important, that now loss of electron is oxidation, gain of electron is reduction. This is a standard, anyway you can remember. Then here O is going out, then that's why it is a reduction. Then this O will go and Zn is required, then it will form ZnO. Then like that only H will remain there, OH was there, O gone with Zn as a ZnO. Then now H will be attached with benzene ring. Then now C6H5 became C6H6, means with benzene ring H has joined. Then now C6H6 complete being benzene structure you can write. That is, then you got benzene from phenol. Okay, C6H5OH, phenol. And this I told you methods of preparing benzene. This is the preparation, actually I told you, preparation of benzene. Three method I told you, one from ethine, one from the salt of acid, benzoic acid, and third from phenol. Now I am going to tell this physical properties. Preparation already told you. Now physical properties. Aromatic hydrocarbons are non-polar molecules. That you remember. Aromatic hydrocarbons are non-polar molecules and are usually colorless liquids. It is liquid. Benzene is a liquid. Okay, colorless liquid or colorless solid, but characteristics aroma means a smell. It has a special smell, characteristics aroma. Okay. Naphthalene, you have seen naphthalene, that this will also, when it is born, it will give, this is sublime actually, sublime. If you heat it directly, it will go to the, from solid to vapor. This is naphthalene. A special odor will be there, smell will be there, a special aroma will be there. Naphthalene balls, naphthalene balls, again here on the naphthalene actually in sometimes where you are putting the cloths, there naphthalene balls, you will generally it is kept white color, okay, because it has a special smell. Moths will not come, insect will not come to there. Naphthalene balls, which are used in toilets also, toilets, and for preservation of cloths, because of unique smell of the compound and the moth, moth, moth repellent property. They will not come to the cloth. Okay, means cloth will be not, you can say their life will increase. Sometimes some insect will come and they will just tear this cloth. Okay, but here that moth repellent property, moth will not come. Okay, they will go far from that, hence cloth will be preserved. Aromatic hydrocarbons are immiscible with water. They will not mix with water, but are readily miscible with organic solvents. With organic solvents it will mix readily. And also this aromatic compounds burn with sooty flame. Sooty flames, it will give flame. Okay. Now I am telling you chemical properties. Arenes means benzene. Arenes are characterized by electrophilic substitution reaction. Main reaction is electrophilic substitution reaction, but under a special condition they also undergo addition and oxidation reaction. Substitution reaction is the main reaction, but in a special condition undergo addition and oxidation reaction. As for example, nitration, I am telling electrophilic substitution reaction. Substitute meaning you are understanding same charge, it can repel with same charge. If positive charge is going, as for example H plus is going, then in its place other H plus group may join. This is important, substitution. If suppose H plus is going, then other group having positive charge will join in the place of H plus. That is called substitution. Okay. Then now I am telling example of and electrophile. Electrophile is E plus. Electrophile is represented by capital E 1 plus, and H is going as a H plus from the this benzene H plus. 6 hydrogen is there in benzene, any one. If one group is coming, only one group, one substituent, then one H plus will go, and its place other one group will come having 1 plus, E plus. That is called electrophile or electrophilic reagent. Okay, then in this H plus will go, and its place other H plus will, other positive group will come, having positive charge. Then here example I am giving you nitration. NO2 will join. NO2 have plus, NO2 have plus charge. Then H plus will go. Benzene from any 6 hydrogen is there, any one will go, H plus will go, and NO2 will come there, will join in its place. Then it will form nitrobenzene. But here that I told you, okay, they will substitute, but NO2 will come from where? NO2 will not, it is not you can't, it is not available NO2 plus NO2. Then you have to bring from HNO3, nitric acid. That is the source of NO2. Then from HNO3, how will you get NO2? That is important things. Then HNO3, you can write like this way also, NO2 and OH, NOH, you can write like this. N from NOH, it is that as, and NO2. Then now it became HNO3, NO2 2O, and this OH 3, and one nitrogen, HNO3. You can write HNO3 as a OH and NO2. Now here what you have to understand, that now you want NO2, then this HNO3 will supply you NO2. Then how? Simply it will not break the bond. Simply it will not break the bond. Someone should be there to break the bond. And that's why you need two things here. Mixture of HNO3 and H2SO4. Mixture of two acid you require. This is called nitrating mixture. Nitrating mixture. Both should be concentrated. Concentrated HNO3 plus concentrated sulfuric acid. H2SO4. Sulfuric acid. Both should be concentrated. It is called nitrating mixture. Then now we will ask, why? What will it do? What is the role of H2SO4? You can ask. And now here, role of H2SO4 I am telling you. H2SO4 is dehydrating agent. Dehydrating agent means it can absorb the water molecule. Then you will ask, where is the water molecules? In HNO3, OH group is there. OH group is there. Then how will it get water? Now you understand. This is very, very important things I am telling you. Mechanism only. Okay, quickly will understand. Now benzene ring has hydrogen. NO2 will go in the place of H. In the place of H. Then that in presence of H2SO4, that H bond will come out from benzene. From the benzene ring, that H, and OH from the HNO3. OH will come as a OH minus. Then NO2 will remain plus NO2, because it has bond has broken and OH has a negative. Then obviously NO2 will have positive. Then this OH minus, now it will go to this benzene ring, near the benzene ring, and it will break that H, that bond will break, and H as a H plus, due to the OH minus and force of this H2SO4 is also there. As soon as H plus will break, OH minus will attract, it will form H2O, and quickly H2SO4 will absorb it. Dehydrating, because H2O is a water molecule. Then this H2SO4 will absorb it. Then now see, as soon as H, that bond has broken, C and H, OH has taken, due to the OH minus, this bond broken actually. And as soon as they form water molecules, quickly H2SO4 is taken. And because H has gone as a H plus, hence that carbon became negative. That carbon became negative because H went without electron, it went. Hence that electron was there on carbon. Then now plus NO2, they require 2 electron. Now this 2 electron on carbon, 2 electron is available, that NO2 will take. Now see how H plus gone and its place plus NO2 joined. Mechanism also I told you. There is a special mechanism I will tell you. Same thing, that will time only a step away I will tell you. Main things now we understood. I think so. Okay. Then NO2 attached to the benzene in the presence of nitrating mixture, and temperature you have to maintain around 100 degrees centigrade. 323 to 333 Kelvin. 323 to 333 Kelvin. Okay. That temperature you have to maintain. Then now you will get nitrobenzene plus H2O. Now same way, three reaction I will tell you, same things will happen. Now only one hint I will tell you, quickly you will understand. Halogenation means Cl2 is there, benzene plus Cl2. Then now in the presence of AlCl3, this anhydrous aluminum chloride, AlCl3, AlCl3 anhydrous calcium chloride. You know that electron deficient, this is electron deficient molecule, AlCl3 is required air condition. Then now here Cl2 is there, Cl bond will break, and when this bond will break, one Cl will take electron, then other will become positive charge, Cl positive. Then how you can understand, same thing will happen, H plus will go, in its place Cl will come. Then now it became chlorobenzene, and that H plus and that Cl minus, Cl2 was there, then that when bond broken, one Cl taken the electron, it became Cl minus, other became Cl positive. Then Cl positive went to the replaced with H plus, with a benzene ring, and H plus now it will react with Cl minus as a Cl. Then you got chlorobenzene, and here anhydrous aluminum chloride is the requirement, AlCl3. In its place other things are also there, FeCl3 you can use, FeBr3, FeCl3, FeBr3, both other can be also, any three, either AlCl3 or FeBr3 or FeCl3, any can be used. Okay, then now you got chlorobenzene. Like that way, sulfonation you have to do. Sulfonation means SO3H you have to attach. SO3H, if it attached with benzene, that is called sulfonation. Then now how will you get SO3H? Then now again you remember H2SO4. H2SO4 you can write OH SO3H. Again you count SO3H. 3 oxygen is there, and OH 1 oxygen, total 4 oxygen, and SO3H, that side 1H, and now OH this side. You can just two part you can write OH SO3H. Then OH, in this OH 1H is there, SO3H, that H is there, a total 4, SO3 and O, 4 oxygen, 1 sulfur, and 2 hydrogen, H2SO4. You can write like this, OH SO3H. Then now this bond will break, this OH and SO3H bond will break, and OH is negatively charged. Then obviously SO3H will be positive. And now again same thing will happen. This positive will go in the place of hydrogen, H plus. Then SO3 will attach with benzene, SO3H attached. Then this is called benzene sulfonic acid. And that H plus and OH minus, it will form water, H2O. Very easy. And now one more reaction I am telling you, fourth one, that is the Friedel-Crafts acylation reaction. Here again same thing will happen. Here again anhydrous AlCl3 is required, aluminum chloride. Actually mechanism time you will see on what I to discuss with nitration, that way their role is there in breaking now first understand with methyl chloride, you will quickly understand. Methyl chloride, benzene plus methyl chloride, this is called actually alkylation because CH3 is the alkyl group. In its place C2H5 also can be there, RCl you can tell, RCl. R may be methyl, ethyl, butyl, pentyl, correct? Propyl, any group. R means maybe methyl, ethyl, propyl, butyl, anything. Then this CH3Cl, as for example you are taking, then this bond will break. CH3 Cl bond will break. Cl is electronegative atom. It will take the electron. It will come Cl minus, so CH3 will become positive. Then now again it will attach to the benzene ring like other reaction. Hence it will form toluene, methyl benzene, that is called methyl benzene, popularly known as toluene. And it will form H plus gone from there, Cl minus, HCl. This is toluene. Same way, if it is ethyl group is there, ethyl group, then same way will happen, ethyl group will attach with the benzene, and it will form just like methyl benzene, it will form ethyl benzene and HCl. It will form other product HCl. H from the benzene and Cl minus, it will form HCl, ethyl benzene. Now another reaction is there, Friedel-Crafts acylation reaction. Alkylation means methyl, ethyl, propyl, that is the alkyl group. Now it is the acylation reaction, ACYLATION, acylation reaction. Friedel-Crafts acylation reaction. Here actually condition you have to both Friedel-Crafts alkylation, Friedel-Crafts acylation, it's a condition you have to remember, anhydrous AlCl3, anhydrous AlCl3. This is the important things. Here what will happen, acylation means here all of you know AlC is a Lewis acid, because they want electron, Then here with benzene ring, if acid anhydride, actually the reaction of benzene with acyl halide, also called acid anhydride, in presence of Lewis acid, its acyl benzene, means forms acyl benzene. Then here you should understand acid anhydride, acyl halide or acid anhydride. Only this you have to understand, all things are same. Then here example of acyl halide, I am telling you that CH3COCl. This only you have to remember. RCOCl you can tell. R, CO group, just like acetone. Ketone group, CO group, that is attached. Then CH3COCl. In the R may be CH3, C2H5, propyl, butyl, pentyl, like that. Then CH3COCl. This is called acyl group, acyl halide. Here it is called acyl halide. Then again here same thing will happen. CO double bond is there, CH3, C and O double bond, and Cl is attached with carbon. With carbon, all three are attached. One side methyl group, other side oxygen, third side Cl, single bond. Oxygen is double bond. Then this single bond, CCl bond will break. Cl is electronegative, it will be negative, and carbon will be positive. Then now same way it will join with benzene. Hydrogen will go, there it will go. It will attach. And H plus, what it came out, it will react with HCl. Hence other product will be HCl. And now see, this CH3CO attached to the benzene ring. Carbon of COCH3 attached to the benzene. This is called acetophenone. Now you can understand why acetophenone, because from that carbon double bond is there, CO. Carbon double bond is there, oxygen is attached, CO, and it is also attached with CH3. Then now in the middle, one side benzene came, other side CH3. One side benzene, other side CH3, in the middle CO group is there, just like acetone group. Ketone, you can, now it become ketone. One side benzene, other side CH3, and in the middle CO. That's why it is called acetophenone. Okay. Now one more example I am telling you, last example, that is the acetic anhydride. Acetic anhydride. Then now what is the anhydride? Then now with oxygen 2 CH3CO group is attached. With one oxygen both side CH3CO is attached, but they are attached with carbon, not with oxygen. CH3CO double bond is there, and one valence is opened. Like that we understand. Then 2 CH3CO group is attached with oxygen. One oxygen and 2 CH3CO group. Both side equal, CH3CO. That's why you are writing CH3CO equal to O outside. Then this again same thing will happen, that one bond will break. CH3CO which is attached with the oxygen, middle oxygen, that bond will break. And then what will happen? CH3CO. Then middle oxygen will go with any one, either left side or right side CH3CO. It will come CH3COO, and H from benzene ring will come. Correct? Because when bond will break, then one CH3CO will get positive charge. Carbon will get positive charge. CH3CO, it is attached with O. Then now when this bond will break, then what will happen? One will get positive charge, other will get negative. Then oxygen part will be negative charge. Correct? Then CH3CO, then that C will be positive and other part will be negative. That's why that CH3CO, then that C will attach to the benzene ring, because that is a positive, hydrogen gone, in its place CH3COH came, CH3COO, and carbon was having positive charge due to the bond breaking. Then it became CH3COCH3, and other part which was became 2 oxygen, that was the negative part, and from that CH3COO negative, that H plus from the benzene will come and join with this. It will form acetic acid. Then it is given 2 product. That this is also a same things, acetophenone. This is also called, main product is acetophenone. One side benzene, other side CH3, in the middle CO. Another product is acetic acid. Same way, if anhydrous, same condition, if a chlorine is there, more chlorine is there, 6Cl2 suppose it is there, because 6 carbon is there in benzene ring. Other example, last example I am telling you, benzene 6 hydrogen is there, then all H can substitute, because chlorine is more, 6Cl is there, then 6Cl plus will be there, then everywhere H will go, H plus, and in its place Cl positive will go there. Then 6 hydrogen gone, 6Cl attached, and from every carbon 1 hydrogen gone, and 6 negative charge was remaining, because Cl was there, na, Cl2, 6Cl2. Then 6Cl minus is there, then all 6C minus will come with 6H came from the benzene, 6H and 6Cl minus, it will form 6HCl, and now 6 chlorine is attached with the 6 chlorine atom is attached with the benzene rings. That's why it is called hexachlorobenzene. Hexa means 6, hexachlorobenzene. It is also called C6Cl6, hexachlorobenzene. HCB, also called HCB shortcut, hexachlorobenzene, C6Cl6. Today again some mechanism is there, I will discuss next class and mechanism. Now I am stopping only here. Thank you.